In this problem, what we want to do is look at the energy as the energy changes throughout different points in this problem. The way that we know this is an energy problem in the first place is that we can see that height is being traded for speed. We look at various points A, B, C, and D, and we want to know what types of energy would be present in those different situations. We see things like springs, we see hills. A question might ask us any number of things. And so what we want to do is go through this question and look at some of the different things that we may be asked. Now, in general, the energy at one point is going to equal the energy at any other point. It's the law of conservation of energy. Since there's no external forces doing work to change the energy, we can say, for example, EA equals EB. So then the next question would be, well, what types of energy would be present at these different points? Well, assuming a standard situation where the initial velocity equals 0, and we just get ever so slightly a nudge, and then our sledder takes off down the hill here, we would have only GPE, or gravitational potential energy, at point A. Now at point B, we've got a little bit of height, because having height gives us GPE. But if you think realistically, you've gone down the hill, you've gotten faster. Since this hill is only 3 meters tall, chances are you're still going to be moving. And if we neglect friction, you're definitely going to be moving. And so we have kinetic energy here. And we'll make a note that we only have GPE at point A. So what we can do is say the gravitational potential energy at point A is equal to the gravitational potential energy at point B plus the kinetic energy at B. Now, because we see the types of energy happening over and over again, it's real important to use subscripts. And also, go ahead and make the initial statement of conserving energy, that the energy at one point equals the energy at another point. Well, at this point, we can start substituting equations and filling in values. Again, using little g as 9.8, or actually we'll be using little g as 10 as the AP approximation. And that would be 1/2 times the mass times the velocity squared. You might notice here, since m appears in every term, that m would cancel out in this calculation. But I'm going to go ahead and run it through with m for purposes of using the absolute energy again later. What I can see here is that I have enough information to calculate the entire energy at point A. And so I can do 80 kilograms times 10 for little g times 8 meters. And then I can do 8 times 80, sorry, that's 80 times 10 times 3 meters, plus 1/2 times 80 times v squared. So at point B, a question we could be asked would be, find the velocity of our sledder at point B. And this would be the equation that would get it to us. But notice how many steps we're in before we can even talk about the velocity at point B. We talk about the energy. Energy is the overriding concept here. Now the reason why I kept the mass in here is because if I work out this side, I can say that there are 6,400 joules of energy in the system. Because we start at the top of the hill and all our energy is all wrapped up in gravitational potential energy, I can say that that's the total amount of energy in the system, 6,400 joules. We'll use that as a shortcut in other parts of the problem. Now if I simplify this, 80 times 10 times 3 is going to be 2400. And that's the amount of potential energy at point B. And you could actually subtract here and say that 4,000 joules are left over as kinetic energy. 1/2 times 80 is 40. So when we bring this down, we'll get 40 v squared. And so that means the velocity, 4 to 1,000 divided by 40 is going to be 100 equals v squared. So the velocity at point B would equal 10 meters per second. But this all starts by us being able to say that the energy at part A is equivalent to the total energy at part B. Now, if we want to look at point C in the story here, we can look at this and say, being that we're at ground level, there won't be any gravitational potential energy. Given that there's no friction to slow our sled down, we can say that we're exclusively having kinetic energy here. So at point A, we said it's all potential. At point C, it's all kinetic. At point B, you've got a little bit of both. Now, you could set the energy at B equal to the energy at C, but it's going to be a little bit easier to say EA equals EC. You can set the energy at any 2 points equal to each other because of the law of conservation of energy. Now we know that energy A is already 6,400 joules. Since it's kinetic energy, we can go straight to substituting 1/2 mv squared. And so we can say 6,400 is equal to 1/2 of the mass. 1/2 of 80 is 40. And then v squared. So 6,400 divided by 40 would give us 160 equals v squared. And you take the square root of both sides. By the time you round off, you'll get 12.6 or 13, if we use 2 sig figs, 13 meters per second equals the velocity at point C. So by analyzing what types of energy we have, we can figure out how fast our object is going. Now if you look at the setup here, it looks like our sledder is going to run into a spring at the end of this, and the spring is going to slow him down. And so we can say that the energy being stored in the spring is equivalent to the energy of the system. Again, you can set any 2 points equal to each other. Since we figured out 6,400 joules was the amount of energy in the system, we can say that the energy at point A is equal to the energy at point D. And I'm moving sideways here. Well, actually, I'll just move it up. We can say that 6,400 joules, again taking the shortcut from the first example, is equal to 1/2 kx squared. You can see in the picture that the spring constant is giving us 30,000 newtons per meter. It's a pretty stiff spring, but hey, we can deal with that. And then 1/2 of k would be 15,000. And so by the time you do some algebra, 6,400 divided by 15,000, take a big square root of it to equal x, you're going to come up with 0.65 meters. And that would be the distance that the spring is compressed as it stops our sledder. So there's all sorts of questions you could be asked. How much energy is in the system? How fast is it going at the true bottom of any hill? How fast is it going at the top of this little hill? But you can completely analyze the system as long as you set the energy at different points equal to itself, because energy is neither created nor destroyed.